Okay, so we just talked about how to find field strength. And now let's talk a little bit about what exactly field strength is and how it relates to this thing, work and voltage, okay? So the field strength is literally how strong of a force there is for every coulomb of charge. If you look at what field strength is, it's the force on a charge divided by the amount of charge. Q1 or Q2, whatever, divided by some amount of charge. This gives you the units of newtons per coulomb. Remember, a coulomb is billions and billions and billions and billions and billions and billions of electrons. It is 10 to the 18th electrons. There are 1 billion sets of 1 billion electrons in a coulomb. Because electrons are really, really tiny. It's not useful to talk about a single electron when we talk about electricity. Later on, it could be useful to talk about a single electron when we're talking about, atoms and the states of the electrons in the atoms and things like that. But for right now, it's not useful because when electricity flows, many, 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 many electrons will be moving. Okay. So the units for electric field are going to be newtons per coulomb. So for instance, if you're told there's an electric field of 3 newtons per coulomb, it means that if I have 1 coulomb of charge, that 1 coulomb of charge will feel a force of 3 newtons on it. Because for every 1 coulomb of charge, there will be 3 newtons of force. If this were a 2 coulomb charge, it would feel 6 newtons of force because there are 2 coulombs, and for every 1 coulomb, there are 3 newtons of force on it. Just like with our mass, there are 9.81 newtons per kilogram of mass. If you are 1 kilogram, you feel 9.81 newtons of force on you. If you are 2 kilograms, you feel 19.62 newtons of force on you when you are on the surface of the Earth. Okay. So I believe there is one type of field I did not teach you about yet. Well, actually, I think we talked about it when we did our Google Meet. But it is parallel plates. These plates are parallel. My ability to draw parallel lines is apparently not great, but these plates are parallel. We know that the lines point directly away from positive and go directly towards negative. Now, if you remember, I told you that for a charge like this, when the lines are going away, I'm not going to draw them all the way around, but the lines are closer together here than they are here. And when the lines are closer together, it means our force is stronger. And when the lines are further away, it means that our force is less, which makes sense. The further away you get from it, the less force you will feel from it. Well, notice these lines stay exactly the same distance apart. They go perfectly straight across. They're all parallel. If they stay the same distance apart, the force everywhere is going to be the same. So if you are a charged particle at A, or a charged particle at B, or a charged particle at C, it doesn't matter. The force on you that you will feel if you are all charged the same in the same particle is the same. The field everywhere inside of here is the same. It does not change. Okay? It doesn't change. It's different for a particle like this. As I get further away, my charge goes down. But here, as I get further away from those charges up there, my field strength does not change. It stays the same. And that's because those lines don't diverge. Let's pretend for a minute that I put all these charges up here. I put all these charges down here. And I decided to create an electric field with a strength of, let's use an easy number, 10 newtons per coulomb of charge. Okay? And I'm going to back up a little bit here so I have a little bit more space. So I decided to do 10 newtons per coulomb of charge. And I'll use a space above it. I'll try to use a space above it. If I have 10 newtons per coulomb of charge, then let's look at what happens when I put various amounts of charge in. Okay, you can see right here. So here I will choose, I'm just going to do 3 and you'll get it. Here's different charges. That's a really bad cue. Let's do 1 coulomb, let's do 3 coulombs, and let's do 5 coulombs. I put a 1 coulomb charge in here. There it is, 1 coulomb. And because it's 1 coulomb, I can find the force on it. Well, the force is going to be E times Q, which is 10 newtons per coulomb times 1 coulomb. Hey, what do you know? That gives me 10 newtons of force. Okay, well, what if I put the 3 coulomb charge in here? I put the 3 coulomb charge in here. This changes to 3 coulombs, and what do you know? I get 30 newtons. And if I finally look at a 5 coulomb charge, and remember, it doesn't matter where these charges are, the strength of the field is the same everywhere, I get 50 newtons. What do you know? If I divide them all, I find the same field strength everywhere. Okay. Why is this something that we're talking about? Well, let's say now that I take this charge and I put it over here. And I'm going to grab that charge. I'm going to push it across the field the wrong way. It doesn't want to get close to the positive plates because it is in fact a positive charge, right? It's a 1 coulomb or 3 coulomb or 5 coulomb. Those are all positives. I don't have to show that it's positive if I don't put negative on it, right? So they're all positives. It doesn't want to be close to that, so I have to apply a force in order to put it over there. Let's think about this. If I'm applying a force and I'm pushing it, it's going some distance. That means I'm doing work on it. That means as I push this charge closer to that plate, it gains energy. Well, how much energy is it going to gain? Well, let's choose an easy number again. Let's make this a 1 meter distance. So there's 1 meter between these two plates. So I'm going to push this thing 1 meter. I'm so strong, ability to apply 10 newtons. All right. So how much energy is it going to gain because of the work I do on it? Right? If I'm doing work on it, it has to gain energy. That's how it works. Work is change in total energy. So I push this 1 coulomb charge 1 meter. Because I pushed it 1 meter, 10 newtons times 1 meter is 10 joules of energy is how much it gains. Okay. What if it was the 3 coulomb charge? Well, it would have been 30 newtons times 1 meter. What do you know? 30 joules. And I think I can just write 50 joules here and you all understand. Because I chose 1 meter, the force and the energy were the same. If I had chosen 2 meters, those numbers would not be the same number, right? These are not the same thing. A newton is not a joule. It's just because I chose 1 meter to try to make things simple that the numbers themselves are the same number, 50 and 50, 30 and 30, 10 and 10. It's not meaningful. A newton is not a joule. So those aren't the same things, right? Well, what do you know? I'm going to do something here, and I'm just going to do what I call normalize the amount of energy. I'm going to find out how much energy there is for 1 coulomb of charge, and just 1 coulomb of charge, if I push it across. Well, 10 joules divided by E total. E total. That's energy. Okay, it's not electric field E, it's E total energy. And let's make a note of that somehow. Let me use a W actually, just so that we're not confusing it with electric field, okay? Work total. And we know work is energy. So 10 joules divided by 1 coulomb gives me 10 joules per coulomb. 30 joules divided by 3 coulombs gives me 10 joules per coulomb. 50 joules divided by 5 coulombs gives me 10 joules per coulomb. Hey, that's pretty neat. That no matter how many coulombs of charge I have, the amount of work it takes to push this thing across this electric field is the same. And so let's flip this idea around. What if the charge started on this side and it was going to move this way? It would lose energy. It would have the ability to lose 10 joules per coulomb. So if it was a 5 coulomb charge, it would have the ability to lose 50 joules. If it was a 3 coulomb charge, it would have the ability to lose 30 joules as it went this way across this electric field. Well, it turns out that this has another meaning. We call this voltage. Voltage is the amount of energy each coulomb of charge has. This is important. It's important to realize that voltage is not energy. Voltage is how much energy each coulomb has. So if I have 2 coulombs, it has more energy than something with 1 coulomb. The other reason this is really important to understand is because when I take something with voltage and I give the voltage 2 different ways to go, it doesn't change how much voltage there is. Because voltage is not the amount of energy, voltage is a measure of how much energy there is per charge. Good job, Kat. Here is what I mean by this. You're going to see this a lot when you deal with circuits. Let's just pretend for a minute, and then I'm going to make another video that's more clear about this, that I have these charges that are moving. I like it when we deal with electricity and you pretend a coulomb is a particle. There's a coulomb, it's moving that way. There's a coulomb, it's moving that way. There's a coulomb, it's moving that way. And now, maybe I've got 2 light bulbs to power. I'm just going to do this for now. There's 1 light bulb. There's another light bulb. This battery that is connected to, by the way, this circuit is completely wrong, right? I'm just going to go, oh, here's a battery. It's connected to this battery. This battery is a, you can't really see that, but this battery is a, I don't know, 5-volt battery. Okay, what does that mean? If this battery is a 5-volt battery and the voltage is going like this, what does not happen, but what you tend to think happens, is that 2.5 volts will go this way and 2.5 volts will go this way. No, 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 no. I can't say no enough. Let's pretend for a second that there's just 4 charges. Remember, these are actually billions and billions of electrons that I am representing with a single 1 coulomb charge. I want you to pretend a coulomb, which is a bunch of electrons, is a particle when we think about electricity. It's just easier this way. So there goes a coulomb of charge, and it gets to decide, I want to go right or I want to go left. So let's pretend 2 of them decide to go right, 1, 2, and 2 of them decide to go left, 1, 2. Did I just split the voltage? No. Why not? Because voltage, 5 volts, will mean that there are 5 joules for every 1 coulomb of charge. So this coulomb of charge has 5 joules of energy, and this one has 5 joules of energy, and this one has 5 joules of energy, and this one has 5 joules of energy. They all have 5 joules of energy. How much total energy do I have here then? I have 20 joules of energy. That's what we're pretending right now. So a 5-volt battery does not tell you how much energy is in the battery. It tells you how much energy each coulomb of charge can supply, how much energy each electron can supply as the electrons flow around the circuit. That's what it tells you. I could have a small battery with a total of 100 joules of energy, or I could have a bigger battery with a total of 200 joules of energy, and they could both be 5 volts. Okay, the voltage is not the amount of energy, it's how strong the battery is, but not how much energy it has, if you want to think of it like that. So again, total of 20 joules of energy. 10 joules decided to go this way, 10 joules decided to go this way. So the energy did split. The energy split. But the voltage didn't, because this one still has 5 joules, and this one still has 5 joules, and this one still has 5 joules, and this one still has 5 joules. So this voltage is still 5 joules per coulomb, which is 5 volts. And this voltage is still 5 joules per coulomb, which is 5 volts. So when my path splits, the energy that each of these is carrying, it doesn't give up some energy to the right and some energy to the left. This particle has to choose, I'm going to go right or I'm going to go left, and it carries its energy with it. So it's important to realize that voltage doesn't split like that. The energy will split, but the voltage will not. In fact, the charges did split, right? The coulombs chose to go different ways. So here I had 4, and then I have 2 and 2. So what we will call current, the current of the electricity, kind of like the water flowing, the water chose 2 different paths. So the current split, the coulomb split, the energy split, but the voltage didn't, because the voltage is defined as the energy that the charge is carrying. And in the next video, I think I'll show you a circuit.